Scientists found a planet 40 light years away. Rocky surface, right size, right temperature. Liquid water might actually exist there. And for years, the entire scientific community agreed, this is the one. This is the planet most likely to have life beyond Earth. So they pointed the most powerful space telescope ever built directly at it. James Webb, the telescope that cost $10 billion and 30 years to build. The telescope designed specifically to answer this one question. Are we alone? And after years of observation, after processing data so complex, it took entire teams of scientists working around the clock after developing brand new mathematical techniques nobody had ever tried before. The answer they got back was not yes, it was not no. It was something far more disturbing. They literally cannot tell. Not because the telescope failed, not because the planet is too far away, but because the star this planet orbits is doing something that is breaking science in ways nobody fully predicted. Stay with me. Because what's happening around this star right now is one of the most important and most unsettling of our stories in the history of astronomy. The planet is called TRAPPIST-1e. And before we talk about what James Webb found, or didn't find, you need to understand why this planet made every scientist on Earth stop what they were doing when it was discovered. 40 light years from Earth. In cosmic terms, that's basically next door. Our galaxy alone is 100,000 light years across, so 40 light years is practically our backyard. And sitting in that backyard is a star called TRAPPIST-1. Small, dim, red, about the same physical size as Jupiter, but made of star stuff. Dense, massive, burning with nuclear fusion. And packed in close around this tiny red star are 7 planets, 7 rocky, Earth-sized worlds, all orbiting their star in the same amount of time it takes us to go on a weekend trip. The innermost planet completes a full year in about 1.5 Earth days. The outermost takes 19 days. Every single one of those 7 planets orbits closer to their star than Mercury orbits our sun. The entire system, star and all 7 worlds, would fit inside the orbit of Mercury with room to spare. Now, you might think, that close to a star, those planets must be burning hellscapes. But here's the thing that changes everything. TRAPPIST-1 is not our sun. It's tiny. It's cool. It's dim. So dim that you would need to stand roughly where Mercury sits in our solar system just to feel the same warmth we feel on Earth. The habitable zone, the distance from a star where liquid water can exist on a planet's surface, sits very, very close to TRAPPIST-1, and 3 of those 7 worlds sit right inside it. TRAPPIST-1e, 1f, and 1g. 3 potentially habitable planets, all orbiting the same star, all close enough that a powerful telescope might actually be able to analyze their atmospheres. No other known star system gives us this. 3 Earth-sized worlds in the habitable zone, packed close enough to their star that telescopes can study them dozens of times per year. This is why the discovery became front-page news around the world in 2017. This is why scientists called TRAPPIST-1 the most important planetary system in modern astronomy. And this is why, when James Webb launched on Christmas Day 2021, TRAPPIST-1 sat near the very top of its observation list. But before we get to what Webb found, we need to go back to the beginning. Because the story of how this system was discovered is almost as extraordinary as the system itself. A Belgian astronomer named Michael Gillen was running a survey in the Chilean Atacama Desert. Not with a massive cutting-edge observatory, with a modest 60-centimeter robotic telescope. He'd named it TRAPPIST, an affectionate tribute to the Trappist beers brewed by monastic orders back in Belgium. He had a list of about 50 nearby ultra-cool dwarf stars to monitor, looking for dips in brightness that might signal a planet passing in front of one of them. Around the 30th star on his list, the telescope caught something, a dip in brightness, then another, then a cluster of dips coming so frequently, so regularly, that they couldn't all belong to the same object. Multiple things were transiting this star, multiple planets. Gillen brought in more telescopes, ground-based observatories across multiple continents, all pointed at the same tiny red star. In May 2016, his team published their first results. 3 Earth-sized planets orbiting an ultra-cool red dwarf just under 40 light-years away. Exciting, but not yet extraordinary. What made it extraordinary was what happened next. NASA's Spitzer Space Telescope locked onto TRAPPIST-1 and stared at it continuously for 21 days. 21 days of uninterrupted observation, watching the same star without blinking. And buried in that stream of data were 4 more planets that ground-based telescopes had completely missed. In February 2017, Gillen's team published the full picture. 7 Earth-sized rocky worlds, 1 star, 3 of them in the habitable zone. The orbital arrangement of these 7 planets is mathematically beautiful in a way that tells you something profound about the system's history. All 7 worlds are locked together in what astronomers call a resonant chain. For every 8 orbits the innermost planet completes. The second one completes exactly 5. and so on, outward through the system, each planet's orbital period falling into a neat ratio with its neighbors. It's the longest unbroken chain of this kind of orbital resonance ever found around a single star. The planets migrated inward through the disk of gas and dust they formed from billions of years ago, and they clicked into place one by one, like beads sliding onto a wire. And the chain has held ever since, for an estimated 7.6 billion years. That makes the system roughly 3 billion years older than our own solar system. This resonant structure is also what allowed scientists to weigh each planet precisely without ever resolving it as anything more than a tiny dip in starlight. As the planets pass each other in their orbits, they exchange tiny gravitational tugs that cause their transit timing to shift by seconds and minutes from what pure orbital mechanics would predict. By measuring those tiny timing variations with extraordinary precision, astronomers could calculate exactly how massive each world is. And the masses told them something critical. These planets are rocky, dense, solid surfaces, not gas clouds, not ocean worlds with no floor. Actual rocky planets with surfaces you could theoretically stand on. TRAPPIST-1e specifically sits right in the sweet spot of the habitable zone, receiving about 2/3 of the energy from its star that Earth receives from our sun. It's the right temperature. It's the right size. It's rocky. It's the most Earth-like candidate world we've ever found. And James Webb was designed specifically to look at it. Here's the dream scenario that scientists had in mind when Webb launched. Light from TRAPPIST-1 passes through the thin shell of TRAPPIST-1e's atmosphere as the planet crosses in front of its star. Different gases absorb different wavelengths of that light. Water absorbs certain wavelengths. Carbon dioxide absorbs others. Methane, oxygen, sulfur dioxide. Each one leaves a distinct fingerprint in the light. By analyzing those fingerprints, Webb could tell us exactly what gases exist in that atmosphere, from 40 light years away, without ever sending a single spacecraft anywhere near the planet. It's genuinely one of the most remarkable techniques in the history of science, and it works. It has worked beautifully on large, puffy, gas giant planets whose thick atmospheres leave strong, obvious signals. The question was whether it could work on small, rocky planets whose thin atmospheres would leave signals roughly 100 times fainter. The answer, for TRAPPIST-1e specifically, turned out to be not yet. And the reason why is something nobody fully anticipated. The star itself. TRAPPIST-1 is magnetically volatile. Its surface is constantly shifting, covered in dark star spots and bright, hot patches that rotate in and out of view as the star spins. Our sun has sunspots too, but the sun is so large and bright that a few dark patches barely register when you're trying to measure the faint atmospheric signal of a transiting planet. On TRAPPIST-1, which is tiny and dim to begin with, those spots and bright patches cover a significant fraction of the visible surface, and they change. Sometimes, during a single transit observation, the star's face looks different at the end of the measurement than it did at the beginning. This matters enormously because of what it does to the data. When scientists measure the light from a transit, they're comparing the star's brightness during the transit to its brightness outside the transit. Any change in the star's surface creates a false signal that mimics the kind of atmospheric absorption they're looking for. Stellar contamination, scientists call it. And on TRAPPIST-1, that contamination arrives at amplitudes of hundreds to thousands of parts per million. The atmospheric signal from a thin, rocky planet's atmosphere, at most, about 100 parts per million. The noise is 10 times louder than the signal scientists are trying to detect. It's like trying to hear someone whispering your name from across a stadium while a rock concert is playing at full volume. And it's worse than ordinary noise, because this stellar contamination isn't random static. It mimics the exact shape and pattern of the signal you're trying to extract. It contaminates the data in the same wavelengths, where atmospheric gases would leave their fingerprints. You can't just filter it out the way you'd filter static from a radio signal, because the interference and the message look too similar. Then, during one of the Webb observations of TRAPPIST-1e, a massive stellar flare erupted mid-transit. A burst of energy from the star's surface that dumped an enormous signal into the data that bore no resemblance to anything a planetary atmosphere would produce. One entire transit observation. Gone. Corrupted beyond salvage. The researchers spent more than a year developing brand new mathematical techniques to try to separate the star's noise from whatever the planet might be contributing. New frameworks, new models, new approaches to data processing that had never been tried before. And after all of that work, the honest conclusion was this. They could not say with confidence whether TRAPPIST-1e has an atmosphere or not. While the campaign to observe TRAPPIST-1e was struggling with stellar noise, Webb was also looking at the other planets in the system, and those results were cleaner, devastatingly, heartbreakingly cleaner. TRAPPIST-1b, the innermost planet, was examined first. Scientists used Webb's MIRI instrument to measure the planet's thermal glow at a specific wavelength, where carbon dioxide absorbs light very strongly. If TRAPPIST-1b had a thick carbon dioxide atmosphere, the way Venus does, its thermal glow at that wavelength would have been noticeably dimmed by the blanket of gas overhead. The measurement came back bright and clean. A thick atmosphere was ruled out at greater than 6 sigma confidence. In statistics, 6 sigma means you'd expect to be wrong about 1 time in 500 million. The innermost planet of TRAPPIST-1 is a bare, airless rock. TRAPPIST-1c, the second planet, received similar treatment. Results pointed strongly away from a thick atmosphere, though not quite as definitively. Then, in April 2026, a paper published in Nature Astronomy delivered full thermal phase curve measurements for both TRAPPIST-1b and TRAPPIST-1c together. A thermal phase curve tracks how a planet's brightness changes as it rotates and shows different faces to the telescope, a far more detailed measurement than a single snapshot. Both worlds emitted heat in patterns consistent only with bare rocky surfaces. Atmospheres with surface pressures even close to Earth's sea level were strongly ruled out. 2 down, then came TRAPPIST-1d, right at the inner edge of the habitable zone, slightly smaller than Earth, the inner planet most likely to have held onto some kind of atmosphere. Published results from 2025 showed a transmission spectrum covering a wide range of wavelengths. After painstakingly correcting for the enormous stellar contamination, the raw data was dominated by signals hundreds to 1,000 parts per million from stellar surface features. What remained was a completely flat line. No methane, no water, no carbon dioxide, no carbon monoxide, no sulfur dioxide, nothing. The lead researcher on that study put it plainly and painfully. TRAPPIST-1d can be removed from the list of potential Earth twins, 3 of the 7 planets, 3 bare rocks, the inner worlds of the most hyped planetary system in astronomy, stripped clean of their atmospheres by their star's radiation. And this concentrated the entire weight of humanity's search for life around other stars onto one world. TRAPPIST-1e, the habitable zone planet, the one where the math works, the one where temperatures could allow liquid water to pool on the surface, but only if it has an atmosphere. There was a moment in late 2025 when it seemed like maybe Webb had found something. When the research team ran their contamination-corrected transmission spectrum of TRAPPIST-1e through a battery of atmospheric models, they found something unexpected. Models that included methane in the planet's atmosphere provided better fits to the data than models that didn't. Not a strong detection, not a clean, unambiguous signal, but a statistical preference. A hint. The data seemed to slightly favor scenarios where TRAPPIST-1e had traces of methane mixed into a background of nitrogen gas. The team cautiously described the possibility. TRAPPIST-1e could be something like a warmer version of Saturn's moon Titan, which has a thick nitrogen-methane atmosphere of its own. They called it a warm exotitan. For a brief moment, it felt like a breakthrough, like the data was finally quietly pointing towards something. Then Sukrit Ranjan, a planetary scientist at the University of Arizona who had been involved in all 3 of the team's published papers, looked at the result from a different angle, and he identified a problem that's almost poetic in its cruelty. TRAPPIST-1 is cool enough, as a star, that methane can exist in the star's own atmosphere, not on a planet, in the star. The outer layers of an ultra-cool red dwarf are so much cooler than the surface of a sun-like star that complex molecules can survive there. And methane in a star's atmosphere leaves spectral fingerprints that look nearly identical to what you'd see if the same gas were sitting in a planetary atmosphere 40 light-years away. So when Webb's instruments detected something that looked like methane, the question that couldn't be answered was, is this signal coming from the thin ring of planetary atmosphere, or is it coming from the star itself mixed in with all the other stellar contamination they were already struggling to remove? Ranjan was direct about his conclusion. Based on the most recent analysis, the tentative hint of a methane atmosphere is more likely to be noise from the host star than a real detection. He was careful to add, this doesn't mean TRAPPIST-1e has no atmosphere. It only means the current data cannot distinguish between a genuine planetary signal and a stellar artifact. 2 possible stories remained. In one, the planet has no atmosphere at all, a bare irradiated rock like its inner siblings, stripped of its air long ago by the star's radiation. In the other, the planet has a thin atmosphere, perhaps mostly nitrogen, perhaps with traces of other gases. That Webb's current observations simply aren't sensitive enough to detect cleanly above the stellar noise. What's definitively ruled out is a thick, hydrogen-dominated atmosphere, a puffy envelope like a mini-Neptune. Webb's sensitivity was more than enough to exclude that. Whatever TRAPPIST-1e is, it's evolved. It's more like Earth or Venus than a gas-rich world. But whether it's a living Earth or a dead Venus, whether it has any air at all, remains locked behind the noise. Here's where science does something genuinely beautiful, even when the data refuses to cooperate. If the star is the problem, and every observation confirms that it absolutely is, then the solution has to involve the star. And the team eventually arrived at an approach that sounds almost too clever. They would use a dead world to find a living one. TRAPPIST-1b, the innermost planet, the one already confirmed to be a bare, airless rock, transits the same star as TRAPPIST-1e. And because TRAPPIST-1b has no atmosphere whatsoever, every single spectral feature that shows up in its transit data must be coming from the star. All of it. Every star spot, every bright patch, every molecular fingerprint from the stellar atmosphere. All stellar contamination, nothing else, because there is no planetary atmosphere contributing anything. Which means TRAPPIST-1b can be used as a calibration tool. A stellar noise filter, the technique called the dual transit method, works like this. When TRAPPIST-1b and TRAPPIST-1e transit close together in time, you observe both. You record the stellar contamination stamped onto TRAPPIST-1b's transit spectrum. Then, you subtract that contamination pattern from TRAPPIST-1e's spectrum. Whatever signal remains after the subtraction, whatever can't be explained by the star, is either the planet's atmosphere or the absence of one. Either answer would be a landmark result. Early tests of the technique in 2024 and 2025 showed it genuinely works. In clean observations, the method measurably reduced the stellar contamination, exactly as expected. The mathematical principle is sound, but there's a catch. The technique assumes the star's surface doesn't change dramatically between one planet's transit and the other. When a stellar flare erupts between observations, which on TRAPPIST-1 happens disturbingly often, the star effectively rewrites its own face in minutes, and the contamination pattern recorded on TRAPPIST-1b's transit no longer matches what TRAPPIST-1e sees. The filter breaks exactly when you need it most. The team is pressing forward anyway. They've outlined a program requiring approximately 15 dual transit observations spread across multiple James Webb observing cycles. With enough data points, the statistics should overwhelm the noise from individual flare events. Ryan McDonald, one of the key researchers, estimated that the next major update on TRAPPIST-1e's atmosphere should arrive somewhere around early to mid-2027. Beyond Webb, new tools are being built with exactly this problem in mind. NASA's Pandora mission, a small dedicated satellite designed to monitor host stars simultaneously in near-infrared and visible wavelengths before, during, and after transits, is specifically engineered to map stellar noise so it can be subtracted from planetary observations more precisely. 3 extremely large ground-based telescopes are currently under construction and will be able to attack the same problem at much finer spectral resolution by separating planetary and stellar signatures using their slightly different Doppler shifts as the planet moves through its orbit. And further out on the horizon, NASA's Habitable Worlds Observatory, projected for the 2040s, is being designed from the ground up to directly image potentially habitable planets by suppressing the host star's light by a factor of roughly 10 billion. Not inferring the planet from the star's light, actually isolating the planet's own light directly. That changes everything. In January 2026, NASA awarded technology development contracts to 7 companies to begin building the engineering required to make it real. So where does this leave us? 40 light years away, on a world that may or may not have an atmosphere, sitting in a habitable zone around a star that won't stop shouting over the signal we're trying to hear, the answer is still locked away. 3 of the 7 planets are dead rocks. That much is certain. And those 3 dead rocks tell us something important and sobering. Red dwarf stars, which are the most common type of star in the entire galaxy, are violent enough when they're young to strip away the atmospheres of their closest planets entirely. The habitable zone planets that survive that early stripping may be the exception, not the rule. If TRAPPIST-1e turns out to be another bare rock, the implications are enormous. The most abundant type of potentially habitable real estate in the galaxy, rocky planets in the habitable zones of red dwarf stars, may not actually be habitable at all. That would mean life, if it exists elsewhere, needs a star more like our sun, which means it's rarer, which means we're more alone than we thought. If TRAPPIST-1e turns out to have an atmosphere, even a thin one, then the opposite is true. Life has a whole universe of potential homes we hadn't counted on. Every dim red star becomes a candidate, and given that red dwarfs make up roughly 70% of all stars in the Milky Way, each potentially hosting their own tight cluster of rocky planets close enough for telescopes to study, the number of places where life could exist becomes almost incomprehensibly large. One planet. One answer that's still missing. And the entire question of whether we're alone in the universe hinges on what's hiding in the noise around a tiny red star 40 light years from home. James Webb looked at a planet like Earth, and something feels off. Not because the planet is wrong, but because the universe is making us work harder than we ever expected just to hear what it's saying. We built the most powerful telescope in human history. We pointed it at our best candidate for life beyond Earth. And the star it orbits is screaming so loudly that we still can't hear the planet whispering back. The answer is in there. We just haven't found a way to listen yet.